back in the previous lesson, we were talking about how to find the area, whether that was area underneath a function, area between that's like caught between two functions, area that's enclosed between multiple functions, or even area that is bounded by functions that are dependent on y. So the reason that that was important is because when we are finding volume of any, well, I guess I shouldn't say any shape, but if we're trying to find the volume of, let's say something that could be classified as a cylinder, even if it's in a regular cylinder like this first shape over here. The way that you find the volume of a shape like this is you find the area of the base, and then you multiply it by the height. Whatever that height might be, even if it's slanted, you take the area of the base and you multiply by the height. And if you look at the figure below, it's kind of like we're taking this area, and when you multiply by the height, you're stacking it on top of itself that many times until you get that entire solid. Where you're taking tiny little changes of that area or of that height and stacking it up. So how do you find the volume of a cylinder? Area of the base times the height. So I want to take a look at this solid. It's not necessarily a cylinder, but it still has some similar qualities to it. It's obviously not the same exact, how do I want to say that? The area of the base isn't exactly the same the entire time, but we have ways to deal with that. So I'm just going to read the paragraph that I have written here, and then we can talk a little bit more. I have written, to compute the volume of a solid body, we are going to divide the body into thin slices. Each slice is practically a cylinder whose volume can be computed by multiplying the area of the base by the height. And if I'm going to just add a little bit to this. If we are dividing this solid into thin slices, those heights are tiny little changes of the height. So, I mean, it doesn't look terribly tiny right now because visually I can't have you guys see that with too tiny of slices. But this slice right here that I have kind of highlighted, that is my quote unquote thin slice. I can find the area of that base, which is a circle, and then multiply by that tiny little slice's height. And the goal is to get these slices to be as tiny as possible. That way, when I calculate the air, or when I calculate the volume, I'm getting as close of an estimate as possible and not overshooting too much or undershooting too much. The more volumes we have, the more accurate we can be. Kind of like with Riemann sums when we were calculating area underneath the curve. The more rectangles we had, the more accurate we could get the estimate. So how do we calculate the volume? We'll calculate the volume of all of these tiny little slices and add them together. So technically, when you're doing repeated addition, we can call that a summation. We'll start at let's go with the first slice and go to the nth slice. And we're adding up all of the little heights. And if you notice the notation off to the side here, I know that it starts at y sub 0, but y sub 0 is the very bottom of that slice and y sub n is the very top of that slice. So I'm going to start with the top of every slice, and that'll be what I call that entire slice. And then to calculate the volume of each of those slices, we're essentially calculating the area of that slice the area of the base. So we'll subtract 1. Yes, this might be the first slice, but I want to calculate the area of the base of it, which I'll use y sub 0 for. Or if I'm at the top, I'd want to use y sub n minus 1. Then times its little height, which is labeled delta y. And again, it'll go from the first slice to the nth slice. Now this is going to give us a rough estimate. So to get the exact volume, we integrate. And I should actually say that that's an estimate, because we can't perfectly calculate those areas or those volumes considering they're not perfect cylinders, but they're cylinder-like. So if I want the exact volume, we integrate. Remember, integration is basically just a nice solid way to get that area underneath the curve. Well, if I'm integrating the area, I can get a nice volume. So we'll find a nice area function. Delta y is essentially just our differential, little tiny changes in y, or little tiny changes in the height. And because these are y values, we'll integrate from the lowest y value to the highest y value. So a to b. And I would like you to go ahead and box this. These could also be dependent on x values. It just depends on how the base of our entire solid body is oriented. But we'll get to that in a moment. Let's go through our steps. First thing that I want you to do is sketch the base region and the cross-sectional slices. So what I mean by that is with these types of solids that we are going to be building, you will have a base for the solid. So like if it was a pyramid, like your traditional pyramid, the base of that entire solid is a square, right? If I were to slice it at any point, look over the top of it, I would see a square. So you could even look up top. If I were to slice any of those cross sections, look over the top of it, I see a circle, right? So we are going to sketch the base region and then draw in the cross-sectional slices. And I also want to label those cross-sectional slices with either delta x or delta y. That way, when I write up my volume integral, I know whether I should have x values or y values in it. And the way that you know if it's supposed to be a delta x or a delta y is each of these problems will tell you how the cross-sections are oriented. So if the cross sections are perpendicular to the x-axis, let me just draw some figure. Let's say that, let's say that this was my shape. That was the base of my solid. If my cross sections are perpendicular to the x-axis, that means that they're going to be crossing the x-axis. So perpendicular. And that would be a tiny little change in my x values. So cross sections that are perpendicular to the x-axis will get labeled delta x. Cross sections perpendicular to the y-axis or cutting through the y-axis are going to be changes in y or delta y. Okay, Then you want to sketch a sample of the cross section because you're going to be calculating, or you're going to be coming up with an area formula for those cross sections, considering we're taking these cross sections, finding the volume of them, and then adding those all up or integrating them. So we need to get the area formula for the cross section, which is going to require you having at least a visualization in your head, but preferably on paper. So sketch a sample of the cross section, and then we want to write a formula for the area of the cross section. A of x if you have a delta x, A of y if it's a delta y. But let's think about it. If my cross section, like I had above, was a circle, my area formula of circle is pi r squared. That's not dependent on x, that's not dependent on y. So what we need to do from there is figure out how to connect the area function to either x's or y's. And that is going to require you coming up with some formula that connects like the actual base region of your entire solid to that formula. And you'll see how to do that in a few examples today. And then from there, all we have to do is set up our integrals, making sure that you have the appropriate bounds. You don't want to get all of this work correct and then accidentally use the opposite bounds than what you were supposed to. If you have x values in your, or if you have x variables inside of your integrand, I should see x bounds. If you have y's inside of your integrand, I want to see y bounds. And then you can integrate. For the sake of making this not the longest video lecture ever, I will use the calculator to integrate these. However, if there's enough room on your paper for you to integrate by hand, please do that. Well, not on this paper, but I'm talking about like in practices. Okay, so let's get our first one going. Compute the volume of a solid whose base is the region between y equals 4 minus x squared and the x-axis. So first and foremost, I'm going to stop there and just get my base region sketched. This is where the cross sections are going to build up from. And you know what, before I even do this, I would like you to have a better visual of what in the world we're even building. So movie magic, I'm going to make something appear. Ta-da! So essentially the base region is like the rectangle at the bottom of this bread, or it's this blue section right here that the cross sections end up building up from. And then the cross sections, we have to be able to find our area formula for that. So going back, let's build our base region. I know what the graph of 4 minus x squared is. It's literally just a parabola that starts at a y-intersect of 4 and then it opens downwards. But I'll plug that here anyway. Okay, so yeah, starts at 4 and then it has x-intercepts of -2 and +2. And remember, it said that this is bounded between, or the base region is bounded between that curve and the x-axis. So I don't need any of that or any of this. Okay. And then it says that the cross sections are perpendicular to the y-axis. Okay, so that means that they are crossing the y-axis. See, I'm drawing like a perpendicular line right there. And I'm going to label these delta y. Okay. So we have our base region sketched with the cross sections in there, and then the cross sections are labeled with the correct delta y versus delta x. It also tells us that the cross sections are triangles with bases that are 1/3 of their height. So I'm going to take this cross section that I took, or that I highlighted, and I'm going to just kind of draw the base of that a little thicker and draw that cross section that would be sticking up into the air off to the side. So this is the base of my triangle that lines up with the graph. Obviously, I'm just like scaling this down a little bit because I don't have enough room to just completely draw that entire section from here to here. And let's see, the base of that gets cut in half from the y-axis. And it says that the base of that entire triangle is 1/3 of the height. So I'm going to keep that information in my pocket to use in a moment here. Or I guess we could even write that down now, but I'm going to hold it in my pocket for a moment. So I need to get the area of that cross section together because I want to be able to find, let me go back to that visual from before. I want to be able to find, pretend that's a bread slice. That triangle's a bread slice. I want to be able to find the volume of that bread slice or the volume of that triangle with, obviously, it has some sort of height associated to it, or width if you want to call it that instead. So that I can find the volume of every single cross section and be able to integrate that. So luckily we have a nice geometric shape here instead of a bread slice, which is not a nice geometric shape. We have a triangle, and I know that the area of a triangle is 1/2 base times height. However, when I try to put that into an integral, I don't have an x, I don't have a y, I have b and h. I want to come up with some sort of relationship to get these variables dependent on, well, in this case, y, because I have a delta y there. But if that's not how they work yet, I could always rearrange my function to make it that way. So I'm going to take a look at the base of my triangle because I noticed that that's what I have highlighted here in my visual. So looking at the base of my triangle, it looks like it's kind of like this x length, right? Let me use red for now. It's kind of like it's measuring the x value from 0 to wherever my function lines up. So if I were to go all the way to that very bottom cross section, it would have an entire length of 2 plus the other section, kind of doubling it. If I were at the, I don't know, let's say I ended up at 1 right here. I don't know if that's actually the length of 1, but this section, it goes from 0 to, again, whatever that x value is, maybe that's 1, and then it's doubling that length on the other side. So it looks like the relationship between the base of my triangle and the base of my entire solid is that the base is twice whatever the x value is. Now, because I want to have a y inside my function, remember our differential is going to be dy because we have a delta y here. I need to rearrange my function, which is this blue graph here. Like that is the x value that we're referring to here. I need to rearrange that equation so that I can go ahead and solve for x and plug that into my little base equation down there. So I'm going to add the x squared to the other side and subtract the y. And then I'll square root both sides. And considering we're just using this to measure length, I don't need to have the negative version of the square root. The positive version will get me what I need. Okay, so we have that the base equals 2 times the square root of 4 minus y. All right, so I have that I can replace inside of my area formula. Now I just need to figure out the relationship between the height and whatever, but I already have that underlined there. It says that the bases are 1/3 of the height. Bases are 1/3 of the height. I can rearrange that to solve for h, and then I already know what b is, so I could just put that b equation in here. So 3 times 2 square root 4 minus y equals h. And I'm going to go ahead and replace that in my area formula, but I'll just write that as a 6. Okay, I've run out of room to simplify up there, so I think I'm just going to write my volume integral and simplify in the integrand. So we have, I'll write the bounds in a second. The area of our triangle, 1/2 base times height, we were able to get that dependent on y. These 2's are going to cancel out, and I'll be left with a coefficient of 6. And then those square roots, square root times square root, the square root's going to cancel, and I'll just be left with 4 minus y. And then I need my differential dy that will represent the tiny little widths of all of our cross sections to get our volume. And then we need to integrate that using the y values. So if I look at the base of my region, the smallest y value is 0, highest y value is 4. And remember, those are going to represent all the tiny little widths of the cross sections that are sticking up in the air. Okay, this is definitely an easy one to do by hand. So if you wanted to pause the video and do that on your own, you are more than welcome to get that extra practice. But we'll also do this in a calculator. Math 9, 0 to 4, 6 parentheses, 4 minus y, dy. Oh, I forgot my extra parenthesis. And we are getting a volume of 48. And that is it. So what I'd like you to do in this next problem is try to pause the video a little bit more often, answer some of these questions on your own before I get to them. That way you're really trying to test your brain to see how much you understood what we did in part 1. All right, so example 2, compute the volume of the solid whose base is a triangle enclosed by the function x plus y equals 1, the x-axis, and the y-axis. Oh, that's not what you guys have on your paper. I'm sorry. I thought I had updated this. 2x plus y equals 2. And right now, I don't really care what direction the cross sections are oriented. I'm going to rearrange that equation in a way that's easier for me to graph right now. And then if I need to rearrange it so that it's dependent on a different variable later, that's perfectly fine. But I want to make the graphing process as easy for me as possible right now. So I am going to go ahead and just make that dependent on y so that I have a nice linear equation that I know how to graph since 8th grade. So that makes this y equals 2 minus 2x. Let's go ahead and graph. So it'll start at a y-intersect 2, down 2, over 1. And I'm just going to elongate that x-axis a little bit. So I'll put a 1 over here and a 2 up here. Okay, so that is the base of our solid, the function 2x plus y equals 2, and x-axis and y-axis bound that entire thing. Go ahead and draw the cross sections in. It says that they are perpendicular to the x-axis. So they should be kind of intersecting that x-axis. And I'm going to label those delta x because we have tiny little widths that are measured with x values. I'll take the base of that cross section and draw my solid off to this, or my cross section off to the side. It says that they are semicircles. And again, I like to make the part of my cross section that touches the base of the entire solid thicker. That way I can kind of try to tell the relationship between them later. And these are semicircles. So sorry if that looks like a capital D, it's actually a semicircle. Okay. So area of a semicircle. I know that the area of a circle is pi r squared, so it looks like I have half a circle, so I'll just multiply that by half. And I know that I need, because I put delta x on my drawing, that I'm going to need to find some sort of way to relate the radius to x values. Not that that is necessarily going to be the immediate relationship, but I do need to get rid of that r and figure out how the radius is related to the base of my solid. All right, so I'm going to draw my radius into my visual here. And I'll even get that kind of like lined up on my graph. So it looks like the radius is a half of that entire base section there. And if I went that entire length of that base section, it looks like it's lining up with whatever the y value is at that x value. So I would say that the radius is half of the y value. Or I guess 2 of the radius would give me the y value, right? And you can even kind of test that out by looking at the very first base here of whatever cross section. Clearly that would end up being the radius here. That lines up with whatever cross section I have there. So 2 of the radiuses would give me that output of 2, which is a y value. Now I need that to be dependent on x, so I'm going to rearrange my equation so that I have an x there. So y, oh, I already have the y. I don't need to rearrange that again. So that's 1/2 times 2 minus 2x, or 1 minus 1x. Okay, so let's get up here, replace the r with 1 minus x. And that's gonna end up getting squared, but because I already said that I'm running out of room and I would like to not do too much thinking in my head, I'm just going to end up writing 1 minus x twice to represent r squared. Okay. And just like I did last time, I'm going to go ahead and simplify this area formula while I'm writing my integrand. All right, so that becomes a pi over 2. Does that seem right? And then multiplying the 1 minus x squareds out. 1 times 1 is 1. 1 times negative x is negative x. That happens twice, so that's negative 2x. And then negative x times negative x is plus x squared dx. Sorry, the only reason I was hesitant before is because I had a pi over 8 in my answer, but I realized I never distributed the 1/2 from the radius formula. So all of my coefficients were just scaled up pretty large, both in the parentheses and outside of it. So we'll get the same answer in the end. The only other thing we need now are the bounds. Remember, these are x values. So look at the base of your entire solid. And what's the smallest x value? What's the largest? Okay. So if you want to integrate this by hand, just remember that pi over 2 is literally just a coefficient. So you can factor that out of the integral if you want, or you can distribute it into the polynomial. It's literally just your traditional integrating. Pi is not a variable. It's a coefficient. So you can do that by hand. I'm going to just do that in the calculator. We'll see what we get. All right, so I'll take that out to 3 decimals. It's 0.52. We'll round that up to a 4. All right. So last thing that we're going to talk about is average value. I think this is something that I promised we'd talk about when we were doing our whiteboarding recently. So I'm just going to read what it says, and then we'll kind of get into visualizing some stuff here. It says the average value is essentially the average of all outputs or y values over a given interval. To find the average value of our function over that interval, we're going to restructure the area under the curve into a rectangle. So looking at this visual off to the side, if I were to try to restructure this into a rectangle, I think I would take some of this area from above and put it over here so that it's more flat. Let's see. I think that might work. I think if I took all of that area right there and put it into this empty region right there, that would probably be a good amount of space. However, do you guys notice that value right there, that kind of looks like the average of all of those outputs? Looks like the average y value over that interval. Well, it is. The height of that rectangle that we just restructured is the average y value, or the average value. Now, the area underneath the curve that I just took, like exactly, we would find that by integrating our function from a to b. But if I restructured that area correctly into that nice rectangle, I could just calculate the area under the curve by taking the height of that rectangle, which is the average y value. And multiplying by the width of that curve, which is just b minus a. And that would give me the exact area underneath the curve, if I've restructured it correctly. Let's pretend that we did it perfectly. So if I want to get the average y value only, I could just divide the b minus a to the other side. Now, remember, this is just a coefficient, so I can put this in front of the integral. And if I'm dividing that to the other side, it would essentially just be 1 over b minus a. Do you remember seeing that in a whiteboarding problem recently? I think it dealt with the bathwater problem. So this formula that we just made is exactly how you compute that average output. Go ahead and box that. We have a formula written down now. So we are going to use this formula in example 3 to help us find the average value of sine of x over the interval from 0 to pi. So first thing I want to do is just, and you don't need to do this every single time you do one of these problems, but I think the visuals are really nice to kind of help you eyeball what you should be getting. So I'm going to draw sine from 0 to pi. I know that sine starts at 0, that pi over 2 is an output of 1, and then sine of pi is 0 again. Okay, so if I were to restructure this area, I think, let me try this. No, that seems a little bit too much. And again, keep in mind that I sketched this graph in the first place, so that's not even perfect. Too little. We'll try one more time. Okay, I think that that might work. Might not be perfect, but I think that that might work. I think this area could probably be restructured in there, and then this area could probably be restructured in there. Okay, so we're trying to find that average y value. This would be a good time for you to try to use that formula on your own and then watch the video after you've tried. So the average y value, and sometimes I like to specify the interval. I'm not going to right now, but sometimes I'll say the average y value over 0 to pi. That'll be 1 over pi minus 0. And then integrate from 0 to pi sine of x dx. And I think I'm actually going to do this one in by hand for once. So that'll be 1 over pi times, the antiderivative is negative cosine. Yeah, if I take the derivative of negative cosine, I get positive sine from 0 to pi. I just move that negative to be the coefficient on the 1. All right, cosine of pi. That's -1. Cosine of 0, that is +1. So we end up getting 1 over pi plus 1 over pi, which is 2 over pi, which is not very helpful for me seeing if my drawing was accurate. So I'm going to turn that into a decimal. 0.636. And then I'm just going to double check to see if I integrated correctly. Ooh. Oh, whoops. I see what I did wrong. I forgot to put a pi up top. I put a 1. Also, that output looked way too small. Okay, awesome. So 0.063, regardless of doing that by hand or with a calculator. And I would say that that's a good estimate up there. My drawing looks slightly above half. So I like it. Let me know if you have any questions. This is the end of this video lecture.